All right. Our main speaker today is Anita Gale. Anita joined the Space Shuttle Program in 1974 with Rockwell International in Downey, California. Most of her engineering career was in payload and cargo integration and included the Rockwell Space Division being bought by Boeing. She was then transferred to Houston at the request of the Johnson Space Center, where she was senior project engineer and associate technical fellow and was reassigned to Boeing commercial crew after Space Shuttle ended. She's since retired and is bringing her expertise to us all here. So please welcome to the screen, Anita Gale.
I muted myself. Oops, now it says I'm muted.
You're good.
Okay. Yeah, I mute myself. All right, cool. All right, thank you. Let me share screen and we'll get going on this. This is the one we want to share. Okay, and okay, can everyone see that? We're good. All right, I see thumbs up. All right, cool. All right, so advancing this briefing. Oops, that's interesting. I'm not able to. Oh, all right. This briefing came from a conference of the American Institute of Aeronautics and Astronautics in August of 2011. So as the Space Shuttle program was ending, and it came about because the then chief engineer of the Space Shuttle program at NASA Johnson Space Center was looking for some way to commemorate success of the Space Shuttle program. And let's just say it came down to me suggesting let's have a whole track of sessions at the Space 2011 conference presented by the American Institute of Aeronautics and Astronautics, which is the engineering technical society for aerospace engineers. And we literally had 12 hours of briefings. You can read the numbers. I think everyone but one is able to see the Zoom briefing, so I'm not going to read every word. And we had briefings from every major system, every major subsystem. We actually could have gone on for another 10 hours with the materials that we had, but we crammed all of this data into 12 hours. And as it points out, 33 papers, 50 speakers. And what I noticed as I listened to, saw all of these presentations, is that there were similar themes that emerged over and over and over again, no matter which system. And we're talking systems like orbiter, external tank, solid rocket boosters, space shuttle main engines, orbital maneuvering subsystem. We're talking cockpit systems all over. By the way, I should let you know, this is an engineering briefing, so it's all words. we have one pretty picture at the end, and that's it. It's a boring technical briefing that was prepared by engineers for engineers. So the vehicle did what it was supposed to do. There are some criticisms, and you can, if you want to come up with questions, then bring that up in the questions. Devil in the details, but that's kind of true of everything. And I presented this briefing to engineers from disciplines other than aerospace, from people who were not in the Space Shuttle program. And it was really interesting to see that some of the experiences and lessons we learned on Space Shuttle happen in other industries. For instance, I presented to a major, to managers in a major oil company, and they started telling stories. And this briefing is condensed from a 2-hour version. And the version that I'm showing now usually takes about half an hour. So I'm going to try to condensify it. I'd like to end a little bit early so you have more time for questions. And I would suggest when you assemble to come up with your questions, we'd also welcome stories from your industries. If any of these points strike a chord with any of you, we'd like to see or hear some of your stories as well. Okay, so this is arranged in 8 categories of themes. So the first theme is management challenges, and what we'll do is we'll show you an overall chart, and then I will emphasize certain items, and we'll color those green. So excellent example of how things are done differently at the end of the program than at the start. When I started on the Space Shuttle program in 1974, some of my Apollo era colleagues were still using these. You remember these things? Slide rules, remember those? I don't even remember, I kind of remember how to work it, but I never had any luck with a decimal point. I mean, literally people were doing, engineers were doing preliminary analyses with slide rules, okay? I don't even know if this is taught anymore. And the computer programs were done with these. Remember these? We call them IBM cards. And we would run analyses with boxes of these cards. And don't trip on the stairs when you go downstairs to take your card boxes to the computer room, because they get all confused. So there are major changes between how the program started and design started in the 1970s. By the time I joined the program in late summer of 1974, the outer mold line, the basic shape of the vehicle, and a lot of the internal workings had already been decided. We were supposed to fly in 1979. We didn't fly until 1981 was the first year we flew. And during those 2 years between 79 and 81, I distinctly remember the adjective that went in front of Space Shuttle whenever we got into the news, which was problem-plagued Space Shuttle program. So we've been through that. Leadership required to make tough decisions. The most explicit examples are there were decisions that were not made that needed to be made, and leadership needed to have strong stomach to make them. One was when, actually I'll tell that story later on. There was a specification that said don't launch on a cold day. Challenger launched on a cold day in January of 1986 and didn't come home in one piece, and neither did the astronauts. There was a tough decision that needed to be made there that was not made. Columbia was launched after vehicles had shown some damage from ice and foam falling off of the external tank, and leadership did not decide to delay the program. We'll talk about actually that accident a little bit later on. Passion being important. For those of us who worked on the Space Shuttle program, it was an incredible privilege. It was more than a job. It was our passion. It was what we wanted to do. It wasn't work. It was literally service to humanity is what we were doing. And that may sound strange when you're talking about a job, but that's how it felt to us. It was an amazing program to work on. Really miss it. And I'm going to presume when I emphasize things, you can read the rest. And you're welcome to ask questions about any of this. Next basic theme we're going to cover is basic design practices, and we'll emphasize these. So an example of the pressure of getting to first flight, remember we were called the problem-plagued Space Shuttle program. The whole world was watching what we were doing, and we knew it. And this was during Soviet times, and the Soviets didn't like what this vehicle was what was supposed to be capable of doing, eventually was capable of doing. So an example is the software was having a lot of trouble in getting to first flight. And the way the software, the avionics software was originally designed is that and I was in payload and cargo integration, so this was important to me, it was originally designed so there'd be some basic flight software, and then for the specific parameters that were involved in the specific systems like cargo or payloads that were involved in a specific flight, you kind of do a plug-in. And I'm not going to name the company, very well-known company, was the avionics system, original avionics system contractor. And they said, prior to flight one, they said, we can save a lot of time if we just integrate all that payload stuff into the baseline flight hardware. So that's what happened. We made schedule a little bit faster because of that. And then the biggest surprise to NASA after flight one was, holy crap, we need to fly flight 2 and 3 and 100 and all that. So big lesson learned, just make things modular because that cost throughout the life of the program, one little decision to get to flight one faster, it cost millions of dollars and time throughout the life of the program. The compounding conservatism, let's actually shorten that one and say making systems not more robust, but more complicated, because everyone was trying to get all of the safety into their own system, and we ended up having safety on safety on safety. Got really complicated there. Well, that's interesting. Why won't it advance? Oh, crap. There we go. Okay, interesting. Mac didn't want to behave there for a moment. Okay, next common theme, basic operating practices. And that test what you fly what you test. Everyone said that. It was amazing. About problems to fix. So at the beginning of the program, when we first started flying, when the folks flying the program at the Cape, at Kennedy Space Center, Cape Canaveral, found there was a broken part or something needed replacing. Remember, we worked for Rockwell. There were Rockwell Sabre jets flying cross country from Downey to the Cape just to bring parts. Like usually overnight, as somebody says at 4 o'clock in the afternoon, Kennedy Space Center time, we need this part, something broke. And there's a Sabre jet flying cross country. Eventually we learned you need to have your logistics inventory at the launch site. So it's right there and they just go to another building instead of having to fly cross country. Putting a lot of the background work of flying the vehicle needed to happen at the launch site. Pay attention to what the vehicle is telling you. So prior to the Challenger accident, the technicians who disassembled the solid rocket boosters just that on cool day launches, there was charring on the O-rings in the solid rocket boosters. Now, the solution to that was very complicated. One solution is just don't fly on a cold day. That's really easy. But the vehicles were all coming back intact, so the managers didn't make that hard decision that we needed to either only fly on warm days or stand down the whole fleet. And there was a complicated modification, which eventually got done anyway after more than 2 years of standing down. But the vehicle was telling us, don't fly on a cold day. And of course, on the Challenger accident, there was a burn through of an O-ring on the solid rocket booster and the whole thing fell apart. On the Columbia accident, or before Columbia accident, I mentioned before, it was noticed that there were chunks of debris coming off of the external tank, hitting the wings. We had an almost burn through of a wing of Discovery. It was repaired, vehicle came back. Again, the managers did not, but the engineers knew, the technicians knew, the managers didn't make the tough decision to actually fix that problem. And in payload and cargo integration, there were always customers asking for more data, more volume, more length, more weight. It was always more. There was only so much data we could handle. There was only so much power, and there were payloads that wanted more power. So we had to change our manifest so that two power-hungry users wouldn't be together. Always customers are going to want more. All right, well, now that's working. So next theme, operating for decades. And a lot of industries operate for decades. We operated 30 years, and no space program had lasted 30 years before this, before Space Shuttle. So one thing you learn pretty early on is, well, I'm sorry, you learn later. So in the 90s, I don't remember the specific problems, but I remember problems would happen. Something really weird would happen. And the younger employees were completely baffled. And something might have happened in like 1996. And one of the people who'd been around in the 1980s would remember, oh, I remember that happening in 1985. And this is what we did to solve it. And that person, we talk a lot in the industry about knowledge capture, that person would not have remembered that thing to document it, aside from the fact that the incident came up and it just kind of dredged it up out of the memory banks. So literally, people don't know what we know. And that happens to me all the time, even outside of the industry. I run a design competition for high school students, which I think we've talked about at an OASIS meeting. And literally, I don't know how I do the things I do in order to run the design competition. So this is true across lots of industries. So the bottom, vehicles, assets used in ways never intended. Wow, I think the mark of a great vehicle is that it does more than you ever expected. And there were so many things we did we never expected, like deploying tethers and retrieving satellites that hadn't worked and bringing them back down to Earth and then launching them again. There are amazing things we did that were never anticipated by the original designers. But we who were running the program were able to make the vehicle do what needed to be done. It's great. And for an engineer, problems like that are fun. That was great fun. Next theme, long-term support. Oops, okay, interesting how sometimes that doesn't work. So laws change and suppliers go out of business. That's important too, but a big one that was a huge lesson learned. A law that changed was the Environmental Protection Agency, late 90s, early 2000s, decided that the foam insulation on the outside of the external tank, that apricot, that stuff that's kind of the color of unsulfured dried apricots. The EPA decided that was a toxic substance and couldn't be made anymore. So the external tank contractor had to find a substitute material. And it was after finding and applying using that substitute material that we started having problems with foam falling off the external tank. Why NASA managers didn't ask the EPA for a waiver for like 4, 6, 8 flights a year. I mean, you're not going to kill butterflies in Brazil by flying one external tank every 2 months or so. Why NASA didn't ask for a waiver, I do not know. But because of that change in that law, we lost the Columbia because it was a hunk of that foam that was the new material that didn't work as well, fell off, hit the leading edge of the wing, very fragile. Plasma came into the wing, and literally a wing of the Columbia orbiter came off. And again, we lost an orbiter, we lost crew. By the way, for those of us on the program, these vehicles were like people too. And I know it sounds weird. Maybe anybody who races sailboats would know what I mean. And I race sailboats too. But if you race a sailboat, you get to learn your sailboat's quirks and capabilities, and it becomes your partner and friend and keeps you safe. And these, even for those of us who never got the opportunity to fly on one of them, not many people did, these vehicles were our friends. So we weren't just losing friends who were in the cockpit. We were losing the vehicles too. And it was, those are pretty hard times to lose those vehicles. And especially when it was just simple decisions that could have saved those vehicles. It's just so sad. I don't know if that happens in other industries, but man, it was bad. Okay, next, process improvements. So we were improving processes all the time. I mean, witness, for those who still see me, the IBM card is what we call those cards that we use. So as computational fluid dynamics came about, we started using that. As better computers came along, we were running our structural analyses and thermal analyses on more powerful computers. We were doing better estimating programs, analysis programs. When computer-aided design came along, we converted all of our hand-drawn, yes, the drawings for Space Shuttle were done on drafting boards. These great big boards with drafting machines, which in their day were really amazing, but compared to computer-aided design, is pretty archaic. It's amazing what was done with rather limited tools. This theme about knowing what to keep and where to make changes, since everything on the vehicle was related to everything else, any change anywhere could have an impact somewhere else. One of the things we never changed, with one exception, adding some instrumentation, but it was like a religion to not change what we call the outer mold line of the vehicle. The outer mold line is analyzed, proven. You don't do anything. You don't stick anything on the outside of the vehicle. You don't cut into it. Keep the outer mold line the same. So that was stuff to keep. So the software that we were running, this quote, software ages like wine, hardware ages like milk. It was said more than once in all of these sessions. As software wears out, we were having some corrosion issues. I mean, we're flying in Florida. It's humid and icky there, and rains, and there's hurricanes. And that we would hire young college grads even in the 2000s to work avionics software. And they were programming computers from the 1970s using 1970s software techniques. But the stuff worked. And changing the computers didn't make sense. On the other hand, changing the displays in the cockpit that did make sense when new technology came along. So it was a balance to know what you could change and what you could not change, or what you shouldn't change. I mentioned earlier, we didn't know how we would use the vehicle throughout the life of the program. We also didn't know what improvements would happen. Who knew that? I mean, we could expect that computers would get smarter and more capable and more usable, and we could do better things with them. But who knew what we could eventually do with computers? Obviously, nobody had any idea. Nobody had any idea that we could replace the analog displays with what we call a glass cockpit. Nobody knew that in the 1970s. So we were assessing what we could improve, what we could not improve. Now, granted, for those of us doing process improvements, and I was one of them, there were a lot of disappointments for process improvements that should have happened and didn't, but those are more NASA management decisions, and I won't disrespect the customer much anymore. So, okay, going on to the next theme, complex vehicles. And oh my, were these vehicles complex. Oops, come on, there we go. So considering how complex this was, I'm sure it was very tempting for the designers at the beginning of the program. They were focusing on the overall aerodynamics, that outer mold line, that crucial outer mold line that would allow us to fly. They were testing aerodynamics. There's some flight regimes actually that could not be tested at the time. Had we had computational fluid dynamics, we could. First flight, there was a flight regime. We did not know if the orbiter would survive. It did, we guessed, but didn't really know. A huge afterthought that I know about, so I joined the program in 1974. And nobody was talking about payload and cargo integration. The whole reason you fly the vehicle is because of what's in the cargo bay, and no one was paying attention. I think people thought that putting cargo into the cargo bay would be like throwing stuff in the trunk of your car, putting a tank on a C5 and you just drive it in and chain it down. And it's not that way at all. Payload and cargo integration, you have mechanical interfaces, you have avionics interfaces. Payloads want power, they want data, want commanding. So there's a lot of complexity, and there were decisions made in the design of the vehicle, specifically the spacing of ribs in the cargo bay. And I'm sure they did that because of load paths for taking the loads off the wings into the vehicle. Sorry if I'm getting too technical here, I apologize. But anyway, to simplify things, so the way payloads were installed on latches in the vehicle is there were bridges between the ribs inside the cargo bay. And if you go to the Atlantis exhibit at Kennedy Space Center, you can see these. It's called a bridge. It fastens on two ribs. The spacing between the ribs was different between every pair of ribs. So a bridge that fit in bay 6 would not fit in bay 9. A bridge that fit in bay 9 port would not fit in bay 9 starboard. So we had a huge amount of hardware. And of course, everybody wanted to use certain bridges, and we didn't have a whole set. We didn't have a whole ship set for every vehicle. So there were some bridges, we were literally going through logistics nightmares to trying to handle which bridges and lashes would be used on the different flights. So there was an afterthought. Payload and cargo integration had to accommodate how the vehicle had been designed for other reasons, and really concerted effort in payload and cargo integration didn't really start until about maybe 1979, 1980. Remember, the vehicle was basically designed by 1973. And then accommodating the customer, the whole reason you fly, really didn't start till 1979. We lived with a lot of expense and a lot of time and a lot of challenge for 30 years because of not paying attention to that early in the overall design. Okay, next, actually, this is the last theme, so I'm kind of on time here. Big lessons learned, kind of getting repetitive here, but let's summarize by saying the vehicles are going to do more than you ever expected. Customers were asking for things that they're asking for capabilities we never expected, aside from asking for more. And there were customers asking for more, like a military payload. It's military, so we didn't know, we didn't even know what it was or when it was going to fly. A military payload that needed a little bit bigger diameter than we had in the cargo bay. We literally were hogging out some of the the hardware in the bottom of the cargo bay so this payload that was not designed to the specification would fit. Darn. But during the life of the program, we got smarter about what we could do with the vehicle, what we could accommodate, and providing benefits that had never been advertised in the beginning for customers. And really, when the program first started, I don't think anybody believed it would be flying for 30 years. We all knew something else would come along about 20 years into the program. Not only something better, not come a better vehicle. Actually, there was a better vehicle that was proposed in. Oops, and it says my internet. There was a replacement vehicle that was proposed in the 1990s, like 1996, and now there was a competition between Lockheed and McDonnell Douglas and Rockwell. Had Rockwell's vehicle been chosen, we would have been flying by about 2009 or so. Instead, the Lockheed vehicle was proposed, and it required an engine that had never been tested with fire coming out the proper end, and that turned into a paper program. And not only did we not have another vehicle 20 years into the Space Shuttle program, but at the end of the Space Shuttle program, we had no vehicles for flying American astronauts. And it was a huge, huge disappointment. Anyway, still, we flew for 30 years and people kept it flying. Just creativity and passion about what we were doing. And ultimately, in the end, it was a great program. Sorry it's gone. We'll do more great things in the future. There's another great little vehicle called the X-37, and I only know from before it became an Air Force vehicle, I know what it was supposed to be able to do, and you're not learning much about it, but I hope sometime we learn about what the, no crew on board, but uses some of the same technology. Let's hope for getting something like Space Shuttle again. It was an amazing, amazing vehicle. And that's the end of my slides, and that's the end of my time. And thank you so much for your kind attention. I understand you're going to break into groups now and come up with questions. And again, not only will I be interested in your questions, but also your stories about similar themes in your industry. So thank you so much.
Thank you so much, Anita. Yes, so we before we go to Q&A, we are going to break out into discussion groups, gives people a chance to A, say hi to each other, and B, come up with some questions. And if you are joining us on Facebook or YouTube, this is also a great chance for you to type your questions into the chat box so we can get them over to Anita here in Zoom. All right, welcome back, everybody. We are going to open up to anyone with questions. You can raise your hand or type it in the chat either here or in Facebook or YouTube. I do want to start off with one of the questions that we got from Allie on Facebook. She's in the U.S. Air Force and is fascinated to hear if you, Anita, have any stories, thoughts about civilian-military partnerships and navigating that relationship. And they're also fascinated by your involvement with the program during the 70s as a woman.
Oh, well, okay. So, wow, I could spend half an hour on these stories. So one story, early on in my career on the Space Shuttle program, I was working in cargo manifesting. And I remember one meeting where we had so we flew military cargo. We flew, at that time, in the 70s, we were flying commercial, I'm sorry, in the 80s, we were flying commercial cargo. We were flying military. And I remember there was a launch window that everybody wanted this launch window. The science guys wanted it for lighting and the commercial guys wanted it for customers. And there's arguing. We finally sorted out. And there are a couple of second lieutenants sitting on the side of the room. And they are there and not saying a thing. And we finally work out this manifest. And then we're doing going around the room, and the lieutenants are asked, well, you know, what's your manifest? And they require a date right in the middle of where the problems were. They were not paying, I mean, they're second lieutenants, they're not paying attention. So sometimes the partnerships were a little bit crazy. It was a shared resource and some folks didn't understand exactly. I mean, and it could have been the second lieutenants were told by their Air Force general, you must have this date because it's my kid's birthday. And we knew stupid stuff like that happen. About being a female in the aerospace biz in the 70s. So I knew going into college that women didn't do that. So I didn't even talk to my high school counselors about what I planned to do because I knew they would discourage me from going into engineering. I had to get absolutely top grades so that no one would question whether or not I belonged there. I would not say I was one of the trailblazers as a female in engineering. I had the privilege of knowing some of the trailblazers, but I was more like a sodbuster, a pioneer, someone going out on the prairie and trying to make a living in a place where no one had ever made a living before. I was in that category. So I was, let's see, when I was at the University of Washington studying engineering enrollment of women passed 1%. So we were like 0.0 something percent, then we passed 1%. I get into industry and there's been 40, 50 years of hardly any women graduating from engineering. So percentage of women in industry when I got into industry was like 0.000 nothing. So I was first woman, only woman, most vintage woman of almost everything I ever did. That's we don't have to go into stories, but we literally, we have a certain vintage. We're figuring out how do you dress, what do you do when the elevator door opens, what do you do when you come to a door with a guy engineer, the guys around secretaries and assistants, but we women engineers were weird. Good question. Thank you. That was fun. Oh, by the way, I'd like to say there was a question in chat about EMI. I apologize. We do acronyms, and there was an answer in chat. Yes, electromagnetic interference. So stuff that has power going through it will emit electromagnetic signals, or I'm sorry, well, electromagnet, let's just call electromagnetism. That's not my field of work. We had some interferences between different boxes in the vehicle that had to be resolved.
Awesome, thank you. Okay.
I'd also like to mention that during the break, those of us who didn't go to the breakout rooms were having some fun discussions about examples of some of the same phenomena that were happening in other industries, like hardware going out of date and that kind of thing. And software from the 70s being used. Alexis was talking about that. All right.
Yep. Yep. Unfortunately, sometimes software from the 70s is still being used today. All right. It looks like CB, you have a question. You can should be able to unmute yourself. Can
you hear me now?
Yes.
Okay. This is for Gail. Thank you for a very interesting talk. This happens on the corporate and on the educational level. I'm curious about your experience on the government level. You know, there are different management hierarchies, and each hierarchy has their own level of decision making. What in your program, what assures or ensures that the problems that are found or the solutions reach the correct decision hierarchy?
Well, the fact that we had 2 accidents that were totally preventable said that it didn't work.
Yeah.
Yeah. And so, okay, I am going to diss on NASA. I'll give you an example of a decision I was involved in directly. One of the process improvements I developed was standardization of interfaces and containerization of cargo in the cargo bay. So, and what this is, it would be the space equivalent of what you see on trucks and trains and ships all the time now. You see cargo containers, right? Most cargo is in containers. So it can just be driven to the ship or put on a rail car, brought to the ship, a crane picks up the container and plops it on the ship and takes it off at the other end. And what that means for the ship is a ship can be import completely unloaded and loaded in about 2 days. Whereas previous to that, even smaller ships than what we see today might require 2 weeks in port to be unloaded and loaded. So there's a huge advantage to having containerized cargo. On the space shuttle orbiters, every cargo complement required latches in different places, power interfaces in different places, avionics interfaces in different places, and literally the aft cockpit, the control panels for controlling or talking to the payloads in the cargo bay. Literally, those whole control panels in the cockpit had to be taken out, reconfigured, replaced. With containerization of space shuttle cargo, instead of taking months to turn around an orbiter, we could have turned around an orbiter in a couple of weeks. We could have saved thousands of hours in the orbiter processing facility, which were very expensive hours. And when we briefed this to NASA managers, they were saying, oh, that's really a great idea, but somebody else should pay for it. United Space Alliance should pay for that. We brief it to the United Space Alliance. Oh, that's really a great idea. Boeing should pay for that. And you brief it to Boeing, it's like, no, the customers should pay for that. And what we realized, going back to management processes, is there are NASA managers at Kennedy Space Center and Johnson Space Center too, who establish or rate or measure their self-worth based on the size of their budget and the number of people working for them. And literally, our idea to save thousands of hours was threatening rice bowls.
Mm-hmm.
We got nowhere with it. And it was exactly
Wow.
the right thing to do. And it's so frustrating to know what we should have been doing, but it never got anywhere. And there's
Wow.
stories like that all through the program. Hope that answers.
That sounds typical, unfortunately.
Yep. Oh, poo.
All right, and FYI, this is from Ali, who asked the question previously on Facebook. She said, Sodbuster is an incredible analogy. So.
Yeah.
Good to meet yourself.
Yeah. All right, next question we have is from Ted. Is X-37 a secret plane? It sounds incredibly capable and useful, yet we don't hear much about it.
Yeah, it'll show up in the news, usually when it lands after having been on orbit a year or two. It's an Air Force space plane. It looks like a little bitty teeny weeny space shuttle. Yeah, it's I actually was involved with design of the cargo bay before it went, as we say in the industry, before it went black. So it was a NASA idea. NASA didn't pursue it, but the Air Force liked it. We had Air Force officers in a lot of our briefings about it. So Air Force picked it up. And there were 3 orbiter processing facility buildings. 2 of them now, it's X-30. If you go on the Kennedy Space Center tour, X-37 is painted all over them. But yeah, it's secret. The other OPF is actually for the Boeing commercial crew vehicle they're processing. And I get little indications from some of my friends who are still in the industry of how some payload processes work, but I'm not supposed to know.
You don't know anything.
Nope, I'm conveniently senile.
All right, next question is from Eric. How do you engineer materials to withstand cooling and heating in space?
Oh, that's really not my department. Really, most of the heating is on launch and entry. And actually how we managed it. So most the biggest impact on the orbiter was expansion and contraction. And how we handled it is by rotating the vehicle. So actually the 45 minutes of cool and 45 minutes of warm, that wasn't the real problem. The real problem is if you always had, every time you came around into sunlight, you always had one side exposed to the sun and the other to the ground. And how we resolve that is literally by it's like putting the vehicle on a barbecue spit. It basically rolled so one side didn't get hot all the time and the other side didn't get cold all the time. There was one flight where they experimented to see what would happen if they exposed one side to heat all the time and the other side to cold all the time. And literally the orbiter, what would you say, distorted so much that we couldn't close the payload bay doors. So there's a big thermal effect. So it's literally, we just rotated the vehicle so we were getting even heating and cooling.
Cool. Next question is from Amaret. What are your thoughts on the best way to provide accountability in a large system without making a process so complex and paper pushing that it becomes unwieldy?
Oh, wow.
Would it be better to work on the cultural and management expectations or try to proceduralize and systemize it?
So, yes, all of that. Because if it's not part of the culture, it's not going to be implemented. Yeah, that's a problem in any organization. I mean, I really literally don't know how to answer it. It's a management challenge. It's a cultural challenge. I think every large organization with complex processes have that. And actually, I do have an answer. So at least in a small sense, we did an implementation, and I don't know why I didn't think of this immediately. When the Space Shuttle Program was moved from Southern California to Houston, we called it the Great Shuttle Migration. And we're here in Houston. You remember the Enron thing where power that was generated in California was moved out of the state and then sold back into the state for more money, which eventually brought the downfall of Enron and all that kind of stuff. Well, literally, it got too expensive to power up the buildings in California with our constantly reducing contract costs or contract value. So the NASA customer had been trying for years to get Rockwell and then Boeing to move the engineering force from Southern California to Houston. And the Enron thing is finally that straw that broke the camel's back. So we moved to Houston. My payload and cargo integration managers knew that this was going to be a challenge. So what we did, or what they asked me to do, and I made a great career doing things other people either couldn't do or wouldn't do because they didn't like doing it. We wrote process descriptions for everything we did in payload and cargo integration, how to run every analysis step by step, how to do every drawing, how to do everything. And when we trained the new engineers in Houston, because only about 18% of us moved from Southern California. Instead, our ex-military managers figured 80% of us would move from Southern California. It's more like 18. So we were training a lot of people. When we trained those people, we trained them with the procedures that we had written about how to do these tasks. And normally the challenge with procedures is you get process creep and the procedures don't keep up. Because we had trained the engineers using the procedures that had already been written, they knew whenever a procedure changed to change, or whenever a process changed to change the documentation. So actually in payload and cargo integration, we were able to keep processes standard and keep things running pretty well. But we were the exception that proved the rule. Hope that answered the question.
Hopefully. All right. Let's see. Can't see. Oh, yes. Amaret's got a thumbs up. So yes, I think that answered the question. Awesome. All right. Are there any other questions? Feel free to raise your hand, put them in the chat.
Or does anyone have a story about similar experiences? Actually, maybe Alexis and Abhishek could retell their stories.
Yeah, I was like, I guess I can retell my story that I'm definitely not an engineer, but I do air quality stuff. I'm an environmental scientist, and one of our air quality programs is from the 1970s, and it does not work on any of our current computers. So that's very fun trying to learn, as someone who's never learned DOS, trying to work a program that was designed on DOS. And
same thing.
Okay.
And Abhishek had another story. Oh, are you muted?
You're muted.
Yeah.
There we go. Got
there.
it. I'm not muted. I'm headset.
Put it up.
So, I mean, I'm a electrical engineer, and we have instruments that come in from the 90s that were designed in the 90s. All the drawings were formerly on paper, hand drawn, like electronic designs, but they were hand drawn. It's kind of unheard of now. So you find these instruments that have been running in the field. They were supposed to come in every couple of years at least to the office for recertification, and they came in after 20 years. So you can understand the problems, and you see the repair issues, and you're trying to hunt down the corners of the office, trying to search for components if they're available, or look up these legacy suppliers. So,
and it's not funny, but when you're in the middle of it, it's horrible. But in hindsight, I mean, it's funny that the same things were happening on the Space Shuttle program as you're experiencing right now. And I'm sure there are other folks on this Zoom meeting who have similar lives.
Ted just shared one. Susan, I see your hand up. I'll get to you in just one second. Ted typed it out, so I want to get to him. But he said, one difference in the private industry versus government is private industry can make some strange decisions for marketing and profit reasons. The oil field service company that he worked for, they had a 3 5/8 diameter downhole tools that were rated to 20,000 PSI. And then they were able to build a 2 3/4 diameter tool that could be rated to 200 PSI as well. But in order to prevent the new tool from making the old tool obsolete, the decision was made to reduce the thickness of the tool and made its rating less than 20,000 PSI. So extra budget was required to make it a inferior tool. So
it's not funny, but it's hilarious.
All right, Susan, you should be able. Oh, hold on. Okay. Oh, okay. I'm not sure what's happening. Try unmuting yourself one more time, Susan.
Oh, there it is. Okay. Okay. I know nothing about the medical industry except for being an occasional patient, but I do hear stories and I do see evidence that I have a doctor who was trying to stay in the paper, the old way of doing things, and she apparently just gave up, just absolutely gave up. So when Ted talks about paper-centered ways of keeping records and all the tech things that are being added to the doctoring industry, I sure hope somebody does an Oasis talk on that, because I'm just imagining they're going to not know how to read our bodies in a short time, figure out what has happened to us in the past. I don't know. Does anybody have any idea what I'm trying to say? I hope.
And I'm not in the medical industry, although it's interesting. There was a program that the medical center, one of the medical center hospitals had, called Pumps and Pipes. And actually the medical center was asking engineers from the aerospace industry to help them on designing and improving some of their medical technology, some of the tools. So they were showing us some of their tools. That's not answering your question, but there are some people in the medical industry who know that they need engineers to design stuff instead of doctors.
All right, I think this will be our last question. It's from Eric. Do you think a reusable vehicle should incorporate a high-end 3D printer to handle parts needs, or put one in on a space station?
Ooh, yes. So one of my good friends is chief engineer for a company called Made in Space. And they actually have 3D printers on International Space Station. They made news a couple of years ago. They 3D printed the first tool in space. It was actually used on International Space Station. And so looking at history, none of us were around in the 1850s for watching the Clipper ships, but we know there were Clipper ships. These are the great multi-masted ships that went from Boston to San Francisco around the Horn, and a quick trip was 100 days. They had to handle everything that could happen between Boston and San Francisco, and they didn't go through the Panama Canal then. So they had to have extra mast and extra sail material and a sewing shop for sails and carpentry shop. They had to have spares of everything that might break on a voyage around the Horn in 100 days, or sometimes half a year. A problem with going to Mars is it takes 200 days, more than 200 days just to get to Mars, and then another similar amount of time to get back. If you carried enough spares for everything that might bust while you're on that voyage, there's not enough vehicle room to do that. So in order to not have to carry a whole machine shop to repair everything that might go wrong on a Mars mission, you need to you need to have 3D printing in space. And actually, Made in Space is looking at how to use the broken part as feedstock to 3D print a new part. And whether they turn the metal or the material from the old part into powder or wire or whatever they need, that would enable not having to carry a whole lot of extra stuff. So yes, we need 3D printing in space. We see discussions of 3D printing in space conferences. I was actually I just came back last night from being the, let's call them the on-site team for a conference called the Space Settlement Summit, where it was a Zoom conference like this, but we learned on large, important complex Zoom conferences that having a little group on site of, we had, I think, 8 of us running this in Las Vegas, and 3D printing in space was part of what we were finding being discussed in that program as well. So yes, great question. Let's do it.
That's really cool. We'll see what the future holds.
Yes.
All right, well, thank you so much. Like, huge thank you for being here today and to answering all of our questions.
Thank you. This is fun. I really appreciate it. Great audience, good questions.
Awesome. Well, we love having you, so thank you.